Welcome back to Basic Electronics. In the previous class, we looked at an op-amp circuit for conversion of a triangular input voltage to a sinusoidal output voltage. We will now take up a design problem based on that circuit. First, we will find the resistance values required for the given specification. After that, we will simulate the circuit from scratch, which includes entering the circuit schematic, setting parameter values, and simulation related parameters. Finally, we will run the simulation and verify that the output voltage is indeed what we would expect. We will also look at the Fourier spectrum of the output voltage to judge the quality of the output waveform. Okay, let us begin. Let us consider this following design problem. A triangle to sine converter circuit is shown, this circuit here, which we have seen earlier. Design the circuit for the following specs. So the same circuit we need to design for a different set of specs. Input voltage 10 volts peak to peak, output 20 volts peak to peak, and the input of course is triangular and the output is a sine wave. And we want the following breakpoints in Vi, that means along this axis: plus minus 1 volt, plus minus 2.5 volts, and plus minus 4 volts. Let us briefly go over the operation of this circuit. What we did first is to plot VO, that means this voltage, as a function of this current I, and that turned out to have this shape here. And then we figured that in this op-amp circuit, Vi and I are related by Vi equal to minus Ra times I, and because of the minus sign, the VO versus I relationship got flipped, and we have VO versus Vi as shown in the figure here. And these are the time domain plots. That is our input voltage and that is our output voltage. So now we want to design the same circuit with 3 breaks. So therefore we are going to have 3 branches like that. We have 2 here, we will have 1 more branch, and of course we need to find out all the component values, this resistance, that resistance, that resistance, and so on. Alright, so this is what our VO versus Vi should look like. And note that we are plotting VO versus minus Vi here, because we know that VO is proportional to minus Vi and not plus Vi. And this expected relationship, the sinusoidal relationship here, shown in the light blue color, is represented by this equation here: VO equal to VO cap, that is the amplitude of the output voltage, which is 10 volts, times sine pi by 2 times minus Vi divided by Vi cap. And Vi cap is the amplitude of the input voltage, in this case 5 volts. Since we know the breakpoints in the input voltage Vi, we can calculate the corresponding breakpoints in the output voltage VO with this equation now. And those values, those breakpoints in VO, are shown in this column here. For example, for Vi equal to plus minus 1 volt, we would have VO equal to plus minus 3.09 volts, and so on. Also, let us take Ra equal to 1 K, and with this value, since I equal to minus Vi by Ra, the numerical values of Vi and I would be the same except for the minus sign, because Ra is 1, and therefore Vi equal to 1 volt would mean I equal to 1 milliamp, and so on. So now we have the complete information about the breakpoints. We know the VO value for each breakpoint and the current value for each breakpoint. Let us now look at the component values that we need to calculate. And as we have seen earlier, because of symmetry, R1A and R1B are equal. Also R1A prime and R1B prime are equal. So the values that we need to calculate are R0, R1, R1 prime, R2, R2 prime, and there would be a third branch because we have 3 breakpoints. So we will also need to get R3 and R3 prime. And we will assume that these diodes turn on at 0.7 volts. We will take this V0 as 15 volts. So this minus V0 would be minus 15 volts. And now let us see what information we already have. We have these breakpoints in the input voltage, and we have calculated the corresponding breakpoints in VO as well as in the current I. Here is the plot of VO versus I, and these are the breakpoints 1, 2, 3. In addition, of course, we know that with I equal to 0, we will have VO equal to 0. And with I equal to 5 milliamps, we have VI equal to minus 5 milliamps, and that corresponds to the maximum value of the output voltage, that is 10 volts. So we have these 5 data points now. What we will do now is to connect the first two with a straight line, the next two with a straight line, and so on, and calculate the slopes S0, S1, S2 and S3. As we have seen earlier, these slopes can be related to the resistance values as follows. The slope S0 is equal to R0, S1 is R0 parallel R1, R0 parallel R1, S2 is R0 parallel R1 parallel R2, R0 parallel R1 parallel R2, and so on. And since we already have computed these slopes now, we can find the resistance values. R0 is the same as S0. R1 can be found using S1 and R0. R2 can be found from S2, R0 and R1, and so on. So at the end of this step, we have all these resistance values, namely R0, R1, R2 and R3. The last step is to calculate these resistances R1 prime, R2 prime and R3 prime for the third branch, which is not shown over here. And as we have seen earlier, these are related to the breakpoints in the output voltage, namely this breakpoint and this breakpoint. For example, this first breakpoint is given by R1 by R1 prime, that is R1 by R1 prime times V0, which we have taken as 15 volts earlier, plus V on, which is 0.7 volts for the diodes, plus V on. Now we already have R1, and knowing this breakpoint in VO, this value here, we can now calculate R1 prime. And similarly, we can get R2 prime and R3 prime. So here are our final results. With V0 equal to 15 volts and V on equal to 0.7 volts, we get the following values for R0, R1, R2, R3 and R1 prime, R2 prime, R3 prime. And you should definitely go through this exercise of calculating these values and make sure that you end up with the same values. You might notice that there is some repetition involved in these calculations, and you might want to write a small program to perform these calculations. It might help. Okay, so now our design is complete, and let us simulate the circuit and make sure that it does indeed work as a triangle to sine converter as we want. This is what our final circuit schematic is going to look like, and we are going to construct it from scratch step by step so that you can also follow and make it up yourself. But before we begin, let us note one specific feature that is very useful in this specific case, and that is we have these global parameters here. For example, V on has been specified as 0.7 volts. Now there is a reason for that. All these 6 diodes are going to be identical, and they have parameters like on resistance, off resistance and V on, and these parameters are going to be the same for all these 6 diodes. And therefore it makes sense to have one global parameter called V on. So suppose we want to change it from 0.7 to 0.6, then we need to only make one change over here. So that is very convenient. So let us remember this feature, and let us now start constructing this circuit schematic. Let us start with defining a few global parameters, and that is done by right clicking on the canvas anywhere and choosing this add global parameters option. And now we are asked for the name of the global parameter, which is V on. Let's add some others, R on and R off. So we will use these for diode parameters. Okay, now let us click anywhere in the canvas, left click, so that the parameters appear here, and now we can edit these. So V on can be 0.7, R on could be 0.1, and R off could be, let's say, 10 mega ohms. And when we bring in the diode now, we can use these parameters to assign as properties of the diode. The diode model that we are looking for in this project is called diode R. So let us bring that in like that. And you see that its parameters are on resistance, off resistance, and V on. It has got some default values. What we will do is to assign the global parameters over here that we defined earlier, like that. And we need 6 of these diodes, so let us copy these. And 3 of those need to be in the other direction. Alright, so now we have the diodes in place. Next, let us get the resistors. The resistor is called R.ECE, so let us bring that in. And we need 6 of these, like that. And now some of these resistances will have the same resistance values, and therefore what we will do is define additional global parameters. For example, R1, R1 prime, etc. Okay, so here are all the resistance values that we have defined: R1, R1 prime, R2, R2 prime, and R3, R3 prime. We have also assigned values to them, and this is of course as per the design that we just completed. Alright, now let us assign these values. So this resistance should get R1, like that. This resistance should also get R1, like that. We can display the property of this resistor, and it shows R1 since we assigned it already, and so on. Let us now start part of the wiring that we need to do. Let me move this component. Alright, now for the wiring, it turns out to be very convenient to use this element called connector underscore E to indicate electrical connector, and we can place it over there like that. It's a dummy element and it's used only for wiring purposes. It doesn't have any physical properties. Alright, so let me move these and place some additional connectors like that. Okay, move this back. So that is what we got, and we will do the same thing for this bank of resistors as well. Okay, so this is what we have got now. We have also brought in this R0 and assigned 3.1K to that. In addition, we have got this R1 prime, R2 prime, and R3 prime as well on both sides, up as well as down. And now we can do the wiring. And so on. Alright, so this is what we have got after some of the wiring is completed. And now we need to connect these 3 nodes together, and that should go to VCC. We also need to connect these 3 nodes together, and that should go to VEE. So let us do that. And note that we have placed one additional connector over here, and we will name that node as VCC. So let us click on this wire and call that VCC. Okay, so we have got VCC here and VEE here. Our next step is to make sure that these nodes are actually sitting at plus 15 and minus 15 volts. And we will do that with a DC voltage source, and that is called VSRC DC box. It's called box because it looks like a box. We need two of these, and we will make one of these the VCC source and the other one as VEE source. Alright, now this one, let us say, is our VCC source. So its plus terminal would be VCC and the minus terminal would be 0. And we will make sure later that 0 is indeed our ground node. For the other source, the plus terminal should be 0 and the minus terminal should be VEE. Let us display the node names. So all we need to do is to right click on the concerned node, add node name text box, and the text box comes over there indicating the name of the node. We can move that with the arrow keys, and if we want finer movement, we can use the control and arrow key. So let us do the same for the other nodes. Next, let us bring in the op amp. We will use the 741 op amp, and in particular let us choose the 741B. Now let us make connections with the rest of the network. This minus terminal must be connected over here, and the output terminal of the op amp must go over there. Okay, so this is what it looks like. We have also added this resistance 1K, and we have named these VCC and VEE nodes of the op amp as VCC and VEE. That means this node is actually connected to this node because they share the same name, and similarly the VEE node of the op amp, which is named as VEE, is actually connected to VEE, although we don't see a wire. We need some more elements. One is the triangle input source, and that is triangle 3 here, and the other one is ground. Okay, we can do some of the wiring. Now the other end of this source must be connected to ground. We can either connect it like that, or we can use ground dummy like that. And let us remember to name this as 0 because we have used that name earlier, and that indicates the reference node or the ground node. Let us set the parameters for this triangle source now. So click on it, and frequency, let us say 250 Hertz. The high level, let's say 5, and low level could be -5. So we have a 10 volts peak to peak triangle source with frequency 250 Hertz. The next step is to select output variables, and we need the input voltage and also the output voltage. We can name this as V in and this as V out. Note that we have named these nodes as in and out. Before we go to the solve blocks, let us display these global parameter values because that would be handy for reference. And the way to do that is right click in the canvas, insert global parameter text boxes, and then choose whichever parameters we like. And then the list of the parameters along with their values will appear over there. Let us now go to the solve blocks section. Add a solve block. We want transient simulation, so make that transient simulation like that. Our Tn could be 10 milliseconds because our time period is 4 milliseconds corresponding to a frequency of 250 Hertz. our delta t constant, the simulation time step, could be a small time step like 0.1 microseconds. And in this case, we are going to use the automatic backward Euler option. So let us remove this and use the backward Euler automatic option. Let us also set a maximum time step of 10 microseconds, like that. And now what we need to do is to bring in the output block. And let us add the variables that we would like to see, namely input voltage and output voltage. Now we are ready to run the simulation. So we click on Run Solver. The simulation is over. Let us choose time as the x-axis and let us plot both of these together, V in as well as V out. And that is what we have got. We can expand one period like that, and that is our input triangular wave, and that is our output sine wave. The input is 10 volts peak to peak and the output is 20 volts peak to peak, as we expected. Let us now look at the quality of the sine output that we have got, and we do that by looking at the Fourier components of the output voltage. So let us bring in another output block, change the name of the file so it does not clash with the earlier one, choose Fourier equal to yes. Let us look at 20 Fourier components. Output variables, let us look at both input and output voltages. And one important specification is this out t start and out t end. The difference between these two should be 1 period. So let us choose out t end as the end of our simulation interval, that is 10 milliseconds, and out t start equal to 4 milliseconds less than that, like that. Let us now run the simulation and look at the input spectrum first. So that is what we got. This is the fundamental, that is the third harmonic, fifth harmonic, seventh harmonic, and so on. Let us now look at the output spectrum. And now we notice that the harmonics have almost disappeared, and that is what we would really like. Let us now look at the diode currents, in particular the currents through D1B, D2B and D3B. So what we have done is we have added 3 more output variables, ID1B, ID2B and ID3B. Let us add these to the output file first. All right. Okay, let us run the simulation and look at these variables now. And what we will do is to plot these variables as a function of V in, because then we will be able to see the breakpoints, like that. So this is the current through the D1 diode, and this here is the breakpoint introduced by that particular diode, and we see that it is -1 volt. This breakpoint is because of D2, and that is at -2.5, and this one is because of D3, and that is at -4. So this is indeed what we would expect, and that means our design procedure is correct. To summarize, we designed and simulated a triangle to sine converter circuit and found the simulation results to be in agreement with the given specifications. You are encouraged to go one step further, hook up the circuit in the lab and look at the input and output voltages on the oscilloscope. It will take some time, but it is always nice to see that what you are studying in theory works in practice. That is all for now. See you next time.